Today we're going to be talking about the CoreSight subsystem. So we're going to go over the things that we worked on since Bangkok and some of the new things, the new support that Mike is adding, currently working on in order to support new IP blocks and some more of the feature-rich configuration that we might want in order to support more complex trace scenarios. So one of the things that really moves things forward is the fixing the power management problems that we've had since the beginning of the subsystem. So this was not a huge deal since we were only supporting per trace scenarios, and as such the CPUs were always powered. But when CPU-wide trace scenarios were introduced, it really caused a problem, because when the CPUs would get idle, you would lose your configuration, and after that, any access to the blocks would hang your board or crash the kernel. So that was fixed. Andrew Murray worked on that when I wrote the slides. His pad Shet needed some modifications, just syntactic modifications. That was fixed, and I folded his set last week, and it will be available for people to use in 4.4 RC1 when it is released on Monday. Our test bed was the Dragon board, so I tested things on that platform. Hopefully it will be generic enough to address most of the test cases or the environments that are out there. So as I said, this is available, or will be available, in 5.4 RC1. Suzuki Pelosi added support to describe CoreSight blocks in ACPI. So we wanted to have a common representation, whether you would boot a system with a device tree or ACPI. We wanted things to look the same. He did his work based on a standard that was published by ARM. The link is over there. So if you are looking to do the same on your platform, following that specification along with the example that was provided with the patch set for Juno should be able to cover most of the cases that that can be encountered. So his work introduced an interesting side effect. What we used to have is on the top. So because we were using a device tree, it was easy for us to simply take the device name, which is the mapping in RAM, along with the name of the device itself. So that was handy. It served us well for quite some time. But when we started adding support for ACPI, we quickly discovered that it would not be feasible to continue enacting that. So Suzuki introduced something that is, in my opinion, cleaner and easier for people to understand. That's on the bottom. If you are nostalgic and really keen on keeping the old representation, the information is there. It's simply as symbolic links. So do an ls-l and you will find exactly the same information. As I said, we haven't modified anything. The information is there. It's just represented differently. So that's on the ACPI front. So that is there. If you're booting a 5.3 kernel, you can use that functionality, and you should see this. CPU-wide trace scenarios, it took me a very long time to figure it out. It landed in 5.3. So this is available now. We can use the CoreSight events and tracers the same way that we would do CPU-wide trace scenarios for any other event. So nothing changes there, and that was important for us. When using trace scenarios, it's I got fooled by that at the beginning, but this is the My app there. The CPU-wide trace scenarios will run for as long as that application is alive. It does not trace that application specifically. That's just how it works in perf. I basically scratched my head for about a week before I figured out that this is how it works. You can call me slow. You wouldn't be the first. There's also a lot of enhancements on the perf tool side. Leo Yan has worked on this. This is actually a slide that was taken from his presentation earlier this week. he's made a lot of progress and improvement on how to read data in order to make what was traced more obvious for people. So this is an example of the instruction and instruction length feature. So I have his new patch set in my inbox. In order to support that, I have to review. He's also working on introducing testing for CoreSight. So it's a basic smoke test that is embedded in the perf environment. So that will be, so there's a patch set for that. You can add it. It works quite well. The only reason that we do not consider it right now for mainline is because it relies on some of the things that Mike is working on for his support of the CTI, CTM IP blocks. And there's more features from Leo. Again, I have patches in my inbox that I have to review, so a lot of enhancement there. If you're interested in those, there was an example. You did some example yesterday in the hacking session, and there was also a full session on that earlier this week. So Leo would be the person to talk to. So this is what I had in terms of what is available or what has become available since Bangkok. Mike will talk to you about his work on supporting CTI and CTM along with this feature that we call complex configuration.
Thank you. Okay, first slide is a quick review of what CTIs and CTMs are for those who may not be completely familiar. The CTI takes in single triggers between devices, or can input or output them. These are then linked via the CTM, which isn't really a component, it's more just wiring. CTM has channels. So if a trigger goes live and it is attached to a channel, it will be distributed across the entire system, and all other output triggers that are attached to the same channel will go live. The CTI drivers have had a few iterations on the CoreSight mailing list. Hopefully we'll get that onto the main mailing list before long, and eventually into the mainline. The CTI drivers themselves, we're only specifying a device tree at the moment to describe CTIs. A CPI support will follow in due course. So this is what we've got for what CTIs look like in the device tree. This is a minimal CTI. If you describe it this way, you've just got a base set of features. The CTI themselves self-describe how many triggers they've got, and this will allow you to just drive those triggers. For V8 cores and CTI, there is an actual architectural definition of precisely how the triggers should be connected. All of the CTIs are implementation dependent and designed at hardware time. So if you've got a CTI for a V8 core with an optional ETM, this is how it's described, and the driver will then build the correct set of input and output triggers and attach them to the various devices. So if you've got a system that isn't a V8 core, it might be something more complex. This is the definition for the ETF, ETR and STM on a Juno system. So we see here you've got each different connection which connects to the ETR. You've got one for the ETF, one for the STM. We completely describe the input and output triggers and the types of function that you might expect for those triggers. And as well as CoreSight components, we can connect to non-CoreSight components. We can connect to, well, CTIs can be connected to anything that's got a trigger signal, so we need a way of describing these anythings. In this case, we simply create connections which have a name. We don't have a link to another component in the device tree because we're not making a direct connection between the CTI driver and the other CoreSight component. But you also note that it's not mandatory to have both in and out signals, and these two bottom connections are we have triggers from the CTI to the watchdog and a counter within Juno. So when we look at SysFS, you can see that once again this uses the newer representation of the CTIs, of the component names in SysFS. You have any CTI related to a CPU will be named according to the CPU, and the system CTIs will just simply increment from 0. So for each trigger connection that we defined in the device tree, you'll have a triggers N subdirectory. If you look in there, you see the signals, the name of the device, and the output signals and types. So that directly maps onto the information from the device tree. So it makes the CTI component that you're looking at, you can explore what it's got, what it's connected to, and possibly how to use it. So there's very basic programming of a CTI. What you really need to do is to be able to attach triggers to channels. And this is a simple example where we attach a trigger 0, channel 0 is attached to out trigger 1 using this command. And now channels can be activated either by triggers going live from the hardware, or the CTI has a software interface that can be used either directly from SysFS or other programs via an API. So this is an example where we'll just set the channel, which will make any trigger attached to that channel go live and have an effect on the hardware, which can be to stop the trace, put a trigger event in the trace stream, or whatever really it's programmed to do. Okay, we come on to something we're calling complex configuration. ETMs especially have a number of registers which allow them to be programmed in very complex ways. For example, AutoFDO uses a strobing mechanism using counters. The work that Matthew's done on CPU-wide trace scenarios required programming up of timestamps with an additional counter to increase the frequency of the timestamps in the system. Now this is an example of how we would set up the timestamps on an ETM, and as you can see, it requires a number of register operations. At the moment, this is hard-coded into the ETM v4 driver, but we're looking at a way of making this a lot more scalable, easier to add new features in. And this is what we call in complex configuration. We're trying to create a methodology where we can do all this at runtime. So one of the elements we've got are what we call device features, and this will be effectively a data table for a given device, such as an ETM, which will describe a feature in terms of the resources it will consume, the registers that are required, and thus we don't have to hard code the programming in. We'll have a routine within the drive that will take this description of a feature and then program it up if it is selected. The second element of complex configuration is board configuration. Now this is fairly important if you want to do things with CTIs. For example, you may need to program up multiple CTIs to work with multiple components, connect them to the ETR. You may want to have a scenario where you hit a kernel panic and effectively stop the trace immediately. So for board configurations, we can look at programming multiple components across a board. Now for a board configuration, we can have multiple board configurations programmed into the system, but only one will be selectable at any one time. What we will have is an additional configuration driver. This will allow additional device features or board configurations to be loaded at runtime. It's important to using the config.fs interface. The selection of these features will remain the same as it is now, using either sysfs if you're programming that way, or APIs that tools such as Perf can use. So you effectively get either boards or features that the tools want to use, and we have a much more flexible system where we can build new features in at runtime and allow experimentation that way. So finally, the intention is to have a set of tooling which will be human readable and human writable, obviously. So this is by no way the final syntax that we're going to use. This is definitely experimental and under development. But you see here what the sort of thing we're going to have. So we can declare resources we want to use, we can declare how these resources relate to registers, and we can declare input parameters where a feature can either use the default values or you can adjust the parameters of the feature as you enable it at runtime. Now, we envisage that most of these sort of features will be related to ETMs because they're the complex component in this system. The board configurations will obviously program up everything, but I think something like CTI doesn't have a great deal of programming needed other than attaching signals. These tend to be on a more system-wide basis. This is where I am at the minute with complex configuration. I'm looking at taking some of the examples that we've already hard-coded into the driver and converting those into the more data-driven system. So that'll where we'll be at phase one. We'll get these hard-coded ones in and selectable using the methods that I've described. The next phase will be putting in the configuration driver that allows us to add new features in, and finally creating the tooling to convert the sort of text files for new configurations and features into the system. And I think that's pretty much it. So if anyone has any questions on anything that me or Matthew said, please go ahead.
So we are in which phase now? Phase 1, 2, 3. So we are in which phase now? The CoreSight config driver is ready or not?
I'm not sure.
So just now you talk about the CoreSight config driver. So the driver is ready or not?
Oh no, we're still working on the configuration driver. That's part of the complex configuration work that's underway. So it's not ready today, but it's part of my development work over the next 6 months.
Okay, so we are still working on the phase 1.
Yeah, we're working on phase 1. Yeah.
Oh, okay, understand. Thank you.
So there was a question. I think initially he talked about the power management enhancements. So what are those? Can you explain? What are those enhancements that you're?
So it's we're using notifiers. We're using notifiers in order to save the context when the CPUs are going down, and when the CPUs are going up, we get a notification that that context should be restored. So basically, the tracers will be stopped as they should be because there's nothing happening on the CPU, so there's nothing to trace, except that we can restore that configuration and start tracing when the instruction pointer continues to execute the same way that it would have been had there not been an interruption of power. The problem there was that the IP blocks would lose power when the system would go idle, and after that, not being configured, we would try to access them, and the CPU would simply stop because you're trying to access a resource that is not there. So it will hang there waiting for something to actually reply to the read request and would just die. So the work that Andrew did actually fixes that.
So what drivers have these hooks, power management hooks? Is it like all drivers, ETM, CTI, everything is having those, or?
Right now, it's just those are the tracers, so the ETMs, because they are associated with CPUs, and the CPUs are the ones that are being set into idle by the idle framework.
Okay.
The rest of the plumbing is kept powered, because you never know which other CPUs will use them.
For example, the CTI, right? It's per core CTI, so I think it requires.
Yeah, the CTIs will have the same power management in. I think the first phase of the driver, I haven't put it in yet, but I need to discuss with Matthew and the guys how best to implement it for CTI as well. But the CPU-bound CTIs will have to have the same management facilities in, and will have the same power management facilities in.
Thanks.
I have a question regarding the trace idea register. So, for example, on the Thunder X2 systems, we have 128 CPUs. So, but the current trace idea register just supports 8 bits. So, is there any plan to update that?
We talked about that. We don't have a solution for that yet. So the idea right now, the only thing that you can do is reduce the amount of CPUs that you're tracing on at the same time using sets or compartmenting your system. We're basically looking for people that have the hardware to help us with this. If you have a solution, just send it to me and I'll be happy to look at it.
The actual CoreSight specification says only 8 bits are allowed and rest are reserved. So, is there any plan to revise this specification to allow more bits?
Not that I'm aware. We talked about that, and right now we do not have any plans for that.
There's some new features coming out from CoreSight from ARM actually. What is the status of those drivers? Like for example, we need to upgrade to APB4 from APB3, that kind of, hardware changes. Would that be any software changes, any drivers changes? If there's any, what's the plan for that?
There shouldn't be any driver changes because did you say you were moving from APB3 to APB4? Yeah, that should be transparent to the drivers because we're simply accessing the memory system, so the underlying hardware should simply allow us to program the hardware fine, yeah. So there's nothing to change in the CoreSight drivers, whether obviously you're going to have your memory system drivers are a different matter, but the CoreSight should be fine.
This one is regarding the CPU debug driver. Currently, it supports whenever a kernel panic occurs, it dumps the state of all CPUs. So, is there any plan to add more features into it? Like, what more can be done with the CPU debug feature?
What more do you want to do with it?
No, I have no idea. I'm just asking you guys. Do you have something in the pipeline too?
I don't know because that I don't know they have new hardware features. If they have new hardware features coming, then we can enhance. But so far that seems like just use the existing registers. Yeah.
Okay. Yeah. Thanks.
It also depends on use cases. If there's things that you're not finding that you need, we'll be happy to add it. We just came up with this to exploit the hardware that was there, and we tried to make it as generic as possible. But if you have a use case that is not covered, that's perfectly valid. Yes?
Any plans to support ELA? ELA? Any plans to support that driver?
Is that ELA, is that a hardware block?
Yeah, embedded logic analyzer from ARM.
We need the hardware.
Yeah, the ELAs, there are ELAs in Juno, but at present I'm not aware of any plans to support that hardware. I mean, you could, if you could in theory map the registers into user space and use it, and program up the CTIs to take the triggers out of the ELA. I'd have to chat with a few people back at home to see if there's any work going on for the later ELAs in terms of drivers and things, but I'm not aware of any at present.
So you mentioned about notifiers. Is that the PM notifiers that the driver is hooking up to? Because what we found is that it does mean that you can't really trace as much as you want to during the low power modes, and the fact that if the driver isn't compiled, then you can't really support it on an external debugger. So there's kind of pros and cons. So
Very true. We've hit the exact same problem. Okay, if there's anything else, then thank you for coming.